I'm recording it right now. Thank you for reminding me, Ms. Shuba. Tomorrow we're going to have another Zoom meeting where we do more exam review. But I thought that today we would spend a little bit more time going over just explicitly the most recent kinetics stuff that I taught you on the YouTube video from yesterday. So real quick, let me get the whiteboard pulled up. Okay, so someone give me a thumbs up or something if you can see the whiteboard right now. All right, I'm getting a couple of thumbs up. All right, so you guys should see the whiteboard. So let's just talk about, oh, and just so you guys know, to make today a little bit more interactive, I'm gonna be calling on folks a little bit randomly to try to answer some questions. What's that, bud?
Something's wrong in the meeting.
On your Zoom meeting? Okay, I'll be right there. Guys, give me 1 second. My child is also in a Zoom meeting for his little kindergarten class. Give me 1 second and I'll be right back. Okay, y'all, so sorry. All right, so the concepts that were covered in that last YouTube video, over kinetics, let's see. We talked about reaction mechanisms. And a reaction mechanism is a series of elementary steps that make up an overall reaction. And the important thing here is that you understand what is known as the rate determining step. Let's see, Ms. Threlfall, can you either through the chat or on your mic ring in and tell us what is meant by the term rate determining step? What does that mean? What is a rate determining step?
Hold on, I'm getting my notes. It's basically the step that determines the rate. Like
okay, and so yeah, so we can think about reactions as if they occur in these steps. And what about the rate determining step makes it rate determining?
It's the slowest step.
Okay, excellent. Yeah, so if you guys remember in the video, I kind of compared the steps that happen to like runners in a relay race. If we think about the whole reaction as a team of relay racers, the whole team is only going to be as fast. They're only going to get across the finish line as quickly as their slowest person. So that determines the rate of the reaction. Two key things that you guys need to be able to identify when you look at these steps, and again, we're about to practice this. I'm just kind of going over all the ideas. You must be able to look at a series of elementary steps and identify what is known as the intermediate. Mr. Thomas Hare, can you either use your microphone or use the chat and talk to us about what an intermediate is when it comes to reaction mechanisms? What is an intermediate?
An intermediate is when as a compound that shows up during a reaction but isn't like contributing to the overall reaction, so it comes and kind of disappears.
Okay, excellent. Yeah, it's like a go-between, right? It gets produced in one step, but then it gets consumed again in another step. So you never see it in the overall reaction. Excellent. And then we also know that we can identify catalysts. And we'll talk about this more in another context later, but in the context of reaction mechanisms, Miss Batchelor, can you tell us what a catalyst is in the context of these steps, these reaction steps? Miss Batchelor, use your microphone or type in the chat. What is a catalyst?
It speeds up a process.
Okay, so yes, that's very true. But in terms of these series of steps, if we break a reaction down into different steps, the catalyst shows up in what way? For example, Mr. Hare just told us that an intermediate is something that gets produced in one step, but then consumed in another step. So you never see it overall. Can you describe a catalyst in a similar way?
Isn't it consumed and reformed?
Excellent. Very, very good. Yeah. So intermediates and catalysts are opposite. A catalyst will get consumed, but then remade again in another step. So overall, it does not change. Very important you guys understand the differences between those two things. Okay, so after reaction mechanisms, we kind of went through the idea of, I'm not sure exactly what I call it. Sometimes we call it a reaction profile. Sometimes we refer to it as an energy profile. So these are these graphs that you guys know look like this, the progress of the reaction on the x-axis and the chemical potential energy on the y-axis. We start with our reactants, which have some amount of chemical potential. We get a little bump, and then this could be one example of a graph. And you guys all know that, let's see, Miss Samantha Stark, can you use your mic or type in the chat? What type of reaction is this? Would I classify this as endothermic or exothermic? Miss Stark. It's exothermic. Excellent job. Yeah, it's exothermic because overall my products end up at a lower energy state than my reactants have. Where'd that extra energy go? It must have gone out to the outside environment. Mr. Sanford, can you tell me what this bump represents right here? Mr. Sanford, what is this little bump in the reaction energy profile? Checking his notes. Please hold. Excellent job. Yeah, it's the activation energy. Okay, we kind of talked about that already. What is the activation energy? Before, you guys understood that it's the energy required to break the old reactant bonds, right? Now we're understanding, we're using a very specific theory to understand how a reaction occurs. We call it the collision theory or the collision model. And, oh, let's see, Miss Cashman, can you talk to me? Miss Majid's asking, is activation energy E sub A? That's exactly correct. That is one term for activation energy. Miss Cashman, can you use the chat or use your mic to tell us, according to collision theory, where does this extra energy come from, this activation energy come from? In what form is that energy originally? Where does this extra chemical potential energy of activation energy come from?
Doesn't it come from the collisions of the molecules?
Excellent.
And they have just right.
Yep, excellent job. So collision theory says that in order for a chemical reaction to occur, you have to, let's say that this is a molecule of something, and let's say here's another molecule. If these are going to undergo this chemical reaction, they have got to be moving fast enough to collide with each other. And they're colliding, you know, they're moving, so they have kinetic energy. And when they collide, that kinetic energy can get converted to chemical potential energy. That's where this activation energy comes from, just like a crash. They crash into each other and that ends up breaking the old bonds. That is where activation energy is coming from. It's coming from this process of the particles colliding. And yes, Ms. Cashman mentioned that collisions, every collision, if the particles are bumping into each other, every single collision is not going to form products. It's not going to be sufficient. Every single collision will not be sufficient to cause the particles to react. There are several conditions that must be true for the particles to react. So Miss Maddie Webb, can you use the chat or your microphone to tell us one thing that has to be true about this collision for the reaction to occur? What is one thing that must be true about the collision to cause a reaction, Miss Webb?
they must collide with correct orientation.
Okay, very, very good. So that's the one that people tend to forget about. So I'm glad that you mentioned it. The particles have to collide in just the right way. I think in my PowerPoint, I was using an example of, like, I don't remember what the example was, but maybe carbon monoxide and O2. So here's a carbon monoxide particle, and here's an O2 particle. I think I said something like this: if these collide like this, oxygen to oxygen, that will not result in a collision. However, if they collide this way, the carbon end collides with the oxygen end, that may result in a sufficient collision, that may result in a chemical reaction. So the idea is that the particles themselves must be facing the right way when they collide. They have to have the correct orientation. So the orientation matters. That's very, very good. And then let's see, Ms. Skolma, can you tell us what else matters about collisions? Not only do the particles have to collide with sufficient correct orientation, they also have to collide with what else, Ms. Skolma?
They must have enough kinetic energy to overcome the activation energy.
Excellent.
Or whatever that's called.
Yep.
Yeah.
They have to have sufficient kinetic energy. They have to be moving fast enough. So whenever they collide, they have to be moving quickly, moving fast enough. Because remember, that collision, that kinetic energy of the particles zooming into each other and colliding is what provides the energy for this bump, for the activation energy little bump here. That's where we get that extra chemical energy. All right. So if particles have the correct orientation, if they collide with sufficient kinetic energy, then the the reactants may indeed react to form the products. And they form like a special structure right here before the reactant bonds have truly broken and before the product bonds have truly formed. We get kind of a mishmash of atoms. Let's see, Mr. Cox, can you tell me what that little mishmash of atoms up here is called before the reactants have broken apart and before the products have formed? What do we refer to that as, Mr. Cox? Checking his notes. Please hold. Someone else can feel free to jump in if you feel like you know what the answer is. We're looking for the term for the general mishmash of chemicals right here. Excellent job, Mr. Killian. Yes, that's correct. We call it an activated complex. Sometimes we also refer to it as a transition state, because it is the general mishmash of chemicals that represents the transition from reactants to products. So sometimes we say that only when collisions occur with the correct orientation, with sufficient kinetic energy, is it sufficient to overcome the activation energy and form an activated complex, that general mishmash of chemicals. All right. So in this context, someone tell me if this is my reaction profile like this. Here's the activation energy. Someone tell me, what does the presence of a catalyst do to this graph? Mr. Mullick, could you tell me, what does a catalyst do to my reaction profile, my energy graph?
A catalyst would, okay, so it lowers the activation energy required.
Yep, exactly correct. So a catalyst helps facilitate collisions. It helps collisions occur more easily. So this activation energy bump becomes lower. A catalyst does not add extra energy to the system. It does not change anything about the reactants and the products and their energy states. All it does is it lowers this activation energy bump to allow the reaction to occur more easily and therefore more quickly. All right. What is, so Ms. Stark is asking, how does it do that? Great question, Ms. Stark. A catalyst, if you remember and we'll look at examples of this later, in a reaction mechanism, a catalyst is a chemical that gets consumed but then produced again. So all a catalyst does is it helps to like facilitate collisions. It helps to get particles to collide together. One example I gave in the lecture video was that a sheet of platinum metal can sometimes form a catalyst for gaseous reactions. So a sheet of platinum could react to certain gases, and the gases could momentarily bond to the surface of the platinum or something, and therefore the gas is kind of fixed in place so that another gas could come in and collide with it more easily. So the platinum here is not taking part in the reaction. Catalysts do not take part in the reaction. They don't get changed by the reaction. All they do is they facilitate collisions. They're like a matchmaker. They bring particles together and make them collide into each other so they can make a new beautiful thing. Catalysts are like matchmakers. They help particles collide. Good question, Ms. Stark. All right, I want to make sure that everyone understands this other type of graph that we have. So on the x-axis, we have kinetic energy. On the y-axis, we have number of particles. We've seen this before with something called a Maxwell-Boltzmann distribution curve. So at a certain temperature, let me call this T1, we get particles that have a certain distribution of kinetic energies. Someone tell me, let's see, Miss New, can you type in the chat or use your mic to tell me how would this graph change if I had a higher temperature? Let's say I want to draw another graph for temperature 2. What would my curve for this higher T2 look like?
It would shift to the right and flatten out more.
Excellent, excellent, excellent. Very, very good. So at a higher temperature, the graph looks something like this. All right. So remember that the definition of activation energy is the energy needed to form an activated complex. Where does that energy come from? It comes from the kinetic energy of particles colliding. So we can represent activation energy as like a little dashed line on this graph. Only particles that have a kinetic energy that meets or exceeds this threshold, we can say have enough energy to, when they collide together, to overcome the activation energy and react. Does that make sense? So you guys can clearly see by increasing the temperature from T1 to a higher T2, I have caused a greater number of particles to be present past that kinetic energy threshold. In other words, by increasing the temperature, particles are moving faster. I'm going to have more particles colliding with enough kinetic energy so that when they collide, they could, if they collide with the correct orientation, they could possibly form an activated complex. Does that make sense? So this is another type of graph to help us understand activation energies and to help us understand how temperature is one way we can increase the rate of a reaction. We have more particles colliding sufficiently to form an activated complex and overcome this activation energy threshold here. Can someone buzz in and can someone, well, let me ask. Okay, bud.
She said she wants us to look for a sphere in the house and I will draw it.
Oh, cool.
Take a picture of it or write it down.
Okay, so why don't you go try to find a sphere,
But then you can take a picture.
and then you can try to draw it. Okay, I'm busy right now.
I don't know how to
Well, do your best, bud.
No, I could just draw a circle.
Okay, that sounds good. Yeah, that sounds great. Okay, guys, sorry about that. Let's see, Mr. Roberts, can you tell me what would a catalyst do to this graph? How would the presence of a catalyst change this graph? What would I have to shift or change about the graph if I had a catalyst present? Mr. Roberts.
Would it shift that activation energy to the left so that more would meet the threshold?
Excellent, excellent, excellent job. Yeah, so this graph really helps us understand how changing the temperature can speed up a reaction and how adding a catalyst can speed up a reaction, because a catalyst would take this activation energy and shift the threshold down to the left so that my activation energy can now be overcome with a lower amount of kinetic energy, okay? So maybe I could call this EA1. That would be the activation energy without a catalyst. And maybe I could call this one like EA2.
I can't draw a sphere.
Buddy, hey, just find a sphere and I'll help you later, okay? So EA2 would represent the activation energy that is there with the catalyst. Okay, so I'll help you draw it later. Okay, why don't you go into the next thing on your schedule?
It's great.
Okay, cool.
Like his yoga.
Okay. Hey guys, give me 1 second. Let me go help my kiddo real quick. I'll be right back. Okay, guys, I'm so sorry. All right, so I think that we have sufficiently reviewed the new material on the notes. So what I thought we would do now is just go over the packet. So let me get my screen share up. Okay, what you guys should be seeing on my screen is the PDF of the packet. Does everyone see that? Someone give me a thumbs up or something. All right, I'm seeing a thumbs up. Okay, yay. Cool.
This is basically just the Minecraft yoga again.
Okay, bud. All right, so first of all, does anyone have any questions? Hopefully you guys have been looking at some of this. So let me remind you that there were like 5, but go talk to Bob. Henry, go talk to Bob about it, okay? There were 5 things I had uploaded: kinetics practice 1, kinetics multiple choice, free response, super problems, and then a practice quiz. So why don't we start with the first? Hey guys, give me 1 second. I'm really sorry. All right. Sorry, I just saw that Miss New asked me a question. Equilibrium. Miss New, don't worry about equilibrium. I told you guys to, if you encounter any questions about equilibrium, to skip that because that is our next unit. Now, I know that there are some equilibrium questions that showed up, but you don't need to worry about that right now, okay? All right. Let's see. I'm just going to go over some of these questions that I think would be most beneficial for us. And I'll do some of these, and then I will also call on some folks. So I'm looking at the Kinetics Practice 1 worksheet packet. I'm looking at this first question here. Let me zoom in a little bit, actually. Sorry, guys, give me a second. Okay. All right, so in this potential energy diagram, which letter represents the potential energy of the activated complex? So we remember that the activated complex is the term for the chemical structure that's formed when we have overcome the activation energy threshold right up here. So the potential energy of that activated complex looks like it's going to be represented by letter B, doesn't it? So there's that one. Question 2, the addition of a catalyst to a reaction will cause a change in the what? Activation energy, right? That's what catalysts do. They decrease or lower activation energy. Question 3, in order for a chemical reaction to occur, there must always be what? An effective collision, a bond that breaks. We don't always need, oh Lord. We don't always need a bond to break because we could just be reacting a single atom as a reactant, right? So we don't always need that. Reacting particles with a high charge doesn't have anything to do with it. Reacting particles with a high kinetic energy, yeah, typically we do want the kinetic energy to be high enough, but some reactions could occur with relatively low amounts of kinetic energy. So all we really need is to make sure the particle collision is effective, it's sufficient. Yes, that does include kinetic energy, but that kinetic energy does not always necessarily have to be super high. It depends on the reaction. Question 4 is a really good one. Given this chemical reaction, 2 iodine atoms reacting to form I2, the stability of the iodine decreases, increases, or remains the same. So stability is all about the potential energy state of the system. Systems that are at lower potential energy states, we say are more stable. So think about this. This chemical process is completely bond formation. So when the bond forms, you guys know that energy is always released out. That's always exothermic. If energy is released, that means that my products are going to end up down here at a lower potential energy state, right? So I know that they have become, therefore, more stable. Lower potential energy more means increased stability. Question 5. Which arrow represents the activation energy for the forward reaction? So forward reaction means that we're just looking at it from left to right. We start with reactants, we end with products. So I want the activation energy for the forward reaction. So just looking at each of these, it looks like letter D would represent the energy given off when the new bonds form. Looks like letter C is just telling me the overall energy of the products. It looks like letter B is telling me the overall energy of the activated complex. And it looks like letter A is telling me the energy that I have got to add to get my reactants to form into that activated complex. So looks like my answer is going to be either A or B. Now, the definition of activation energy is the extra energy I have to add to the system to form an activated complex and get the reaction to proceed. So is that A or B? It's going to be A. B tells me what the energy is overall up there, but activation energy is how much energy I have to add above and beyond what's already there. So that's going to be this change. So the answer there is A. Okay. Here, which arrow represents the part of the reaction most likely to be affected by the addition of a catalyst? We all know that's activation energy. That's this, this arrow B here, it looks like. Okay, this one actually has numbers. This will be good for us to practice looking at the numbers of the thing. So what is the difference between the potential energy of the reactants and that of the products? Well, the reactants start at 20. Looks like the products end at 40. So that's just going to be the difference there is 20. The answer is A. You know what? These are seeming really simple to me. So I'm wondering if we could go on. Okay, yeah, let's let me find a good question for us to go over. This packet does have a few things that do ask about equilibrium. So if you come across those questions, please just feel free to skip it. 17 might be a good one for us to go over. So let's look at it real quick. So we have this chemical reaction. It looks like the combustion of propane. And they're telling me all this stuff about adding methionol. That is completely irrelevant to the question. I just wanted to know a potential energy diagram for this reaction. I want to point out to you guys that this reaction seems to have energy written here as a product. Let's see, Ms. Shupa, can you, through the chat or with your microphone, explain to me what does it mean when I have energy written as a product? Does that mean that it's an exothermic process or an endothermic process? Ms. Shupa, what do you think? When energy is written as a product like that, is it exo or endo? Exothermic, that's exactly correct. Very good. Because it is as if energy is given off as a product. Very good. And this is combustion, and everyone here should know that combustion reactions are typically exothermic. So all I want to do is draw an exothermic reaction profile. So I start my reactants at some amount of energy. I have my activation energy bump, and then because it's exothermic, my products end up at a lower potential energy state. This here is the amount of energy given off. So that would correspond to this difference between the product energy and the reactant energy. I would say that this is a value of negative 2219.2 kilojoules, just like that. All right, so that's pretty simple. All right. There was another question I thought was a good one. Question 24. I know I'm kind of skipping around. I'm just trying to hit as many good questions for us to review as we can. Okay, so let's go over this. So we have this reaction of gases. Gas A reacts with gas B to form gas C. We want to decrease the rate by increasing something. We want to decrease the rate of the reaction by increasing something here. We have these gases in this apparatus. It looks like we can change the pressure and the volume. So how can I slow down the rate of the reaction by increasing something? So first of all, let's think through what we know for sure already. Oh Lord. Okay, so sorry. Well, let's go through here and think about things that we can eliminate. The temperature of the reactants. By increasing the temperature, am I going to decrease the rate? No, we've already talked about typically increasing the temperature will get the reactant particles to be moving more quickly with more kinetic energy, causing more collisions, and more collisions that have sufficient kinetic energy to overcome the activation energy barrier. So that's a crappy answer. I'm looking for how I can decrease the rate. Increasing the temperature will increase the rate. What if I increase the concentration of reactant A? Well, we don't know for sure, but we do know that most reactions, the rate depends on concentration, doesn't it? The rate law for this would look something like this. So we know that by increasing the concentration of A, we're probably going to be increasing the rate. So we're looking for something, once again, that can decrease the rate. So that's a bad answer. That leaves pressure and volume. Well, I want to think about this. What do you guys think is going to happen if I kind of put more pressure on this little plunger to cause the pressure of the gases to increase? If I increase the pressure, do you think that is going to slow the reaction down? Ms. Haley Young, what do you think about option A? Do you think it's a good answer or a crappy answer? Excellent job, Ms. Young, you're exactly correct. By increasing the pressure, I'm going to cause more collisions to occur, which will probably increase the rate of a reaction according to collision theory. So that's a crappy answer. So I'm left with increasing the volume of the reaction chamber. That's going to be the thing that is going to slow the rate down. Think about this. Concentration is moles per liter. So if I increase the volume, that decreases the concentration, therefore decreasing the rate, which is exactly what I want to do. So by increasing the volume, I decrease the concentration, decrease the rate. Another way of thinking about it is, you guys know that pressure and volume are inversely related. If I increase the volume, I know that the pressure has therefore got to go down. And if the pressure goes down, I know that that represents fewer collisions of gaseous particles. Fewer collisions means slower reaction, okay? All right. This first packet is pretty simple. Why don't we move on to the, well, let me just go through here and see. Again, skip any equilibrium questions. Oh, look, there are answers. Okay. All right, so this is the multiple choice packet. Let me try to find a good one. Okay, I'm looking at question 10 because this is a reaction mechanism question. This is going to be a good one for us to go over. So question 10 here. So I am reacting CHCl3 with Cl2. The overall reaction can be written in these steps. Looks like step 1 and step 3 are fast. Step 2 is slow. So right now I know that step 2 is my rate determining step. So let me see who I want to call on. Mr. Jam. If this is my rate determining step because it is slow, can you describe to me how that allows me to figure out what the rate law is? How can I look at the rate determining step and then write a rate law from that? Any ideas?
Give me a second.
By recognizing this is the rate determining step, how can I use that to help me write the rate law?
So you would need both, like, two of the reactants from the slow step.
Okay.
Which you would find an E and B. Well, yeah,
Okay.
you would find an E and B.
Okay. All right, excellent. So here's the key idea, guys, and this is really important for you to understand. When you have the rate determining step, so remember that the general form of a rate law is like this. This is the differential form of the rate law, right? So remember that these exponents need to be determined experimentally. Well, that is not the case if you have the mechanism and you know the slow rate determining step. These exponents actually end up matching the stoichiometry of the rate determining step. So I would expect my overall rate law then to be K times the concentration of Cl to the first power, because there's a 1 here. The coefficients, if and only if you know the rate determining step, your rate law exponents, the order on the reaction, will match the coefficients. And then this other one has a coefficient of 1 as well. Unfortunately, this does not seem to be any one of my answers. And it looks like the trouble is with this Cl right here. This Cl, Mr. Hibba, can you tell me what that Cl is? In the whole reaction mechanism, this single atomic, it's not Cl2, it's Cl, the atomic chlorine is supplying or it is acting as a what?
An intermediate.
Excellent job. So right here in this reaction, we need to recognize that Cl is an intermediate. Mr. Wilkins, can you tell us how Mr. Hibba was able to determine that Cl here is an intermediate? Mr. Wilkins, any thoughts?
Oh, sorry.
You're good. Yeah, so how did Mr. Hibba know that this Cl here is acting as an intermediate?
Because it gets produced and consumed in the steps.
Yep, that's exactly correct. Yeah, very, very good, Mr. Wilkins. So I can see here that this step 1, the fast step, is producing 2 moles of atomic Cl. And I can see that in the other steps, step 2, 1 mole gets consumed, and then in step 3, another mole gets consumed. So it's an intermediate. That's the very definition of an intermediate. It is a chemical that gets produced but then consumed again. So I am not allowed to have an intermediate in my rate law. So the fact that my rate determining step, my slow step, has an intermediate in it, I cannot use that. What I have to do is think through, where did that intermediate come from? And what I can see is that it came from step 1, didn't it? It came from Cl2 reacting. So what I'm going to have to do is figure out how I can replace Cl in this rate law that I've written with my rate determining step. How can I replace that intermediate with a non-intermediary substance? Well, I can see that my rate determining step uses 1 mole of Cl, and this step 1 has gotten me 2 moles of Cl. So I can replace, in my rate law, I can replace that with, if this step produces 2 moles of Cl, and I know my rate law just needs 1 mole of Cl because it's got to follow the stoichiometry of this rate determining step, then I know that my rate law is going to correspond to me replacing this with this, but I just need half of this step, don't I? my rate determining step just has 1 mole of atomic chlorine. This step produces 2 moles of atomic chlorine. So I just need a half of this to swap in for my intermediate. So my actual rate law then is going to be K. What produced the intermediate? It's Cl2 reacting. How many moles of Cl2 do I need to get 1 mole in my rate determining step of Cl? I just need a half. So we haven't seen an example like this. This is a really good one for us to go over. I can see that I'm actually going to have a half power. It's going to be a half order with respect to Cl2. Isn't that funky? So the answer ends up being E, just like that. That one was a little bit complicated, but you have got to you've got to be able to determine what the rate determining step is, write a rate law based on that, and then if there's an intermediate, you have to get it out, replace it with something that was produced in a fast step. Ms. Farnay, I see you've asked a question. If the slower fast step isn't given, how do we determine which step is the rate determining step? You don't. You can't. So you have to, it has to tell you which one is slow or fast. Ms. Farnay, actually, I take that back. There could have been a question that maybe gave us this. Ms. Farnay, maybe they give us this rate law. They say, hey, here's the rate law for the reaction. And then they do not tell us which steps are slow or fast. Then you would have to recognize that this corresponds to the stoichiometry of this. And so you could recognize that step 2 must be the rate determining because it's determining the rate. Mr. Wilkins, could you also write it as CHCl3 having second order and Cl2 having first order? So Mr. Wilkins, you are asking me if I could just get these both to be nice even numbers by multiplying this by 2 and this by 2. Can you do that? I'm gonna have to get back to you on that, Mr. Wilkins. I've not thought about it like that before. My gut instinct tells me no, but I don't know if I have a good reason for that right now. Let me do some research and I'll get back to you, Mr. Wilkins. Good question. Ms. New is asking, does what we use to replace the intermediate need to be on the right side of the equation? The left side? So my intermediate, so my rate law is always going to be written from the perspective of reactants. In this rate determining step, sorry, I have a lot going on my screen right now. Let me erase some things. In my rate determining step here, I had atomic chlorine as a reactant. So that's the first thing I did was I wrote my rate law using that, using 1 up here because there's 1 mole. But then I recognized that that's an intermediate that came from this fast step. So I needed to be able to swap in. I can't have an intermediate. I need to be able to swap the intermediate with another reactant. So I'm always going to be using a reactant to swap in for my intermediate. Okay. Any questions about this one? This was a really good question to go over. What we could practice doing also is maybe writing what the overall reaction is. So this is something you guys should be used to doing. We had to do it with Hess's law where we have steps and we cancel things out. So it looks like I have 2 moles of gaseous Cl as reactants. I have 2 moles as a product there. That tells me right away that those are intermediates, right? And then I have CCl3, 1 mole of that shows up on the product side and 1 mole that shows up on the reactant side. So it looks like CCl3 is also an intermediate, isn't it? It gets produced but then consumed again. So I have 2 intermediates here. I have Cl and I have CCl3. Do you guys all see how those are intermediates? They get produced but then consumed again. And I can't cancel anything else out. So it looks like my overall reaction for this would be Cl2 plus CHCl3 yields HCl plus CCl4, just like that. And it should be balanced. And yeah, that is indeed balanced. All right, so this is the overall reaction, and these are the steps of that reaction, and we've just shown why E would be the rate law for that reaction. Any questions at all about that? Okay, let's find some more good questions to go over. Okay, question 12 looks like a good one. Once again, some more rate law stuff. Oh my God. Okay. So here's the mechanism, express the rate of the overall reaction. So right away, I recognize that this is my slow rate determining step. So the rate law comes from the stoichiometry of that. A to the second power, concentration of C to the third power. And now I need to pause and make sure that that C is not an intermediate. It does not look like to me the C is an intermediate, because it is true that I get some of it that's produced in this fast step here. But it looks like C is a reactant in that step. So C is truly not an intermediate. It is a true reactant. So that is going to be a good rate law, I believe. So the answer should be E once again. All right. Okay, so this should be pretty simple for you guys. Activation energy, enthalpy of reaction. All this stuff is old crap that we don't care about. Okay, let's go on to a different packet. Free response questions. Ooh, this is good. So I had a question from somebody. Someone emailed me and asked me, so your AP exam is going to be only free response questions. So when I give you tests, we have 2 units to go over, right? So we have kinetics. You guys are taking that test on Friday. Then we have equilibrium that you'll take a test over in a week or 2. When I give you those exams, are they just going to be free response, or am I going to include multiple choice as well? I'm still going to include multiple choice questions in the exams I give you, because I feel like multiple choice is still important for you all to practice and to be able to go over, to really understand the concepts and practice your skills. So I think multiple choice, even though it won't show up on the actual AP exam, I think it's still an important skill for you guys to have. Okay? All right, buddy. Why don't you go get a snack and then work on... Yes, sounds great. How was yoga? Cool. Thank you, bud. All right, you know what? It might be worth our time to do this 1997 question in its entirety. So why don't we work on this? All right, so here it looks like I have 4 different experiments. Did we work on part of this already? I don't recall if we did or not. And here's a chemical reaction. And it looks like I have initial rates of reaction. So I can determine the order of the reaction and write the rate law. All right, so we should practice doing this. This is an important skill, the method of initial rates for chemical reactions. So I know that the rate law is going to be like this, right? R equals K, concentration of A to the N times B to the M. I want to know what those exponents are. So remember, this is the way that we determine the order of the reaction and the reaction rate law in the differential form. We have to use the method of initial rates. So remember, what we're going to do is look for 2 different experiments where one thing has stayed the same and the other thing has changed. It looks like from experiment 1 to experiment 2, B has stayed the same. A has tripled. What has happened to the rate? Really simple. If I divide the rate of 2 by the rate of 1, that will give me a ratio. I know that we've done these examples in the past, but we want to get on to some new parts of this question. If I divide these, I get a ratio of 3 as well. So right away, we can see that by tripling the concentration of A, I have tripled the rate. Therefore, I know the rate must be directly proportional to the concentration of A. So that tells me then that the order on A must be a 1. Remember, if you can't think through that math, you can write out a full ratio. Just write out the rate of 2, 1.2 times 10 to the negative 3, excuse me, 1.3 times 10 to the negative 3 equals K times the concentration of A is 0.75 to the N times the concentration of B is 0.75 to the M. Divide that out by, experiments 1 data. Everything will cancel out except for this N that you'll be able to then solve for. And it ends up being a 1. I triple A, that triples the rate. N has got to be 1 here. So I've just determined that. So I know that R equals K times A to the first power times B to the M power. And now that I know that, I can just figure out what the order of B is. So from reaction 2 to reaction 3, I can see that I've doubled A and I've doubled B. So I know already that doubling A should double the rate. I wonder what doubling B did to it. So once again, I'm going to compare the two rates. Rate 3 compared to rate 2. Rate 3 is 5.3 times 10 to the negative third. Rate 2 was 1.3 times 10 to the negative third. If I do that, I get a 4. And remember what we said? We've said that doubling A, because it's first order on A, that should double the rate, but the rate quadrupled. So quadrupling is 2 doublings. So I know that 1 doubling has come from me doubling A. Where'd the other doubling come from? I doubled B, didn't I? So I know that B must also be first order. I know I did that kind of quickly, but this should be old news to you guys. You all should be familiar with how to do this. So now I now know that it's first order with respect to those. Okay, I could then go and plug in one of these experiments. I know the rate, I know the concentrations, I know the order. I could solve for K to write the rate law. Okay. The initial rate of change in experiment 3 of A. So the rates here are reported as rates of formation of C. And I know that C is getting formed at a rate such that for every 1 molecule of C, I consume 2 molecules of A. So in experiment 3 here, the consumption of A should be twice this. In other words, we could say 1/2 the rate of A is equal to the rate of C. Therefore, the rate of A has to equal 2 times the rate of C. That just comes from the stoichiometry. That's where I got that 2 from right there. You guys need to be able to translate related rates, relate between rates of things. Really very simple. I know that whatever is happening with A has to be twice what is happening with C, because for every 1 molecule of C I produce, I only consume, I consume double the A. So the rate with respect to A must be twice this. All right. Part D would just be plugging and chugging here. Part E is the new thing I want to go over. So which reaction mechanism is consistent with the rate law that we developed in part B? Well, in part B, we used the method of initial rates to determine that the rate was first order with respect to both of them. Just like that. So I am looking for a rate mechanism, a reaction mechanism that would have a rate determining step that matches this. So the rate determining step in 1, it has 1 mole of A, which would match this, but then it has M. It looks like in this mechanism, M is an intermediate, isn't it? M gets produced, but then consumed again. So, and that intermediate came from A and B reacting together. So this M here, I would have to replace with A and B, which would give me 2 moles of A, which would require my rate law from my rate determining step to have a 2 up here. So I know that that is not a good reaction mechanism. So that one is crappy. Let's look at 2. So it looks like my rate determining thing is right here. And that has an A and an M. It has 1 mole of A. I like that. Uh-oh, I have an intermediate though. I can't have an intermediate in my rate law. Where did the intermediate come from? It came from 1 mole of B. So that is consistent with this. So it looks like mechanism 2 is going to be the mechanism I want. Let's check mechanism 3 and see what we think about that. Mechanism 3, here's my rate determining step right here. And once again, we can see that it has 1 mole of A, and it has an intermediate. Where the intermediate come from? It came from this fast equilibrium step, which has 1 mole of A and 1 mole of B. So overall, that would get me 2 moles of A and 1 mole of B, which is not consistent with the rate law. So the answer here is 2. You guys getting the hang of this? These are proposed mechanisms. We know that this is the rate law because we determined it from this data up here using the method of initial rates to find the differential rate law. And now we can use that to evaluate these different mechanisms. I know it has got to be this one because the overall rate law has got to match the stoichiometry of the slow rate determining step, 1M and 1A. I can't have an intermediate. Where did M come from? It came from 1B. 1A and 1B, 1 and 1. All right. Okay. This question works just like that one, so let's not waste our time there.
Daddy,
What's up, Ben?
I forgot how to spell first.
First is F-I-R-S-T. First. Good job, Ben.
I-R-S-T.
Correct. You guys wish your life was that simple. Your biggest problem is trying to spell the word first. Okay, let's look at this one. The reaction between NO and H2 is believed to occur in this following 3-step process. Write a balanced equation for the overall reaction. That's just going to be me canceling crap out, right? So anything that shows up on the reactant side and the product side overall, I can cancel out. So it looks like N2O2 is a product and a reactant there. That's an intermediate, right? We're already thinking about that. It looks like N2O is a product and a reactant there. And I think that's all I can cancel out. So it looks like on the left side, on the reactant side, I'm going to have NO, NO, H2, H2. So 2NO plus 2H2. It looks like I'm going to get from that an N2 and 2H2O. And that is a balanced equation. So that is good. Identify the intermediates. What is an intermediate? Remember, it's something that gets produced but then consumed again, so it never shows up in the overall reaction. N2O2 got produced and then consumed again. N2O got produced and then consumed again. So my intermediates would be N2O2 and N2O. For this mechanism, a student correctly reduces at the rate law is given by this.
Daddy,
What's up, Ben?
how can I select
You're
how
okay,
can
bud.
I erase that R? So I went too far.
It's okay, bud. Just mark it out.
No.
Well, dude, you used a marker. I'm sorry, that's what happens when you use a marker. You can't erase it. You're gonna have to mark it out and try it.
No.
Okay, go ask Bobby for help. Here, but you're doing great. That looks really good. I love your drawing too. It's a struggle over here, y'all, right now. Okay, let's look at the rest of this question. The student concludes the reaction is third order, and the mechanism involves the simultaneous collision of two NO molecules and an H2O molecule. Are the conclusions 1 and 2 correct? So this is a really important question. This is probably the hardest one on here. Let's make sure that we talk about it. So we wanted to make sure that we evaluate the student's 2 conclusions. Number 1, the reaction is third order. Is that a true statement? It is a true statement. We know that overall the reaction is third order because this exponent is 2 and this is 1. Overall it is third order, so that's good. So we think that conclusion 1 is correct because he has done that correctly. The overall order of the reaction is the exponents added. Statement 2, the mechanism involves the simultaneous collision of 2 NO molecules and an H2 molecule. Is that correct? Let me call on somebody. Mr. Pop, what do you think? Is conclusion 2 here a correct statement, or should we disagree? What do you think, Mr. Pop? He's claiming that that in order for this reaction to occur, we need 2 NO molecules to collide at the same time with a single H2 molecule. Is that a good conclusion? Mr. Ian Pop. Ms. McGill, what do you think? Do you think this is a good conclusion or not? Conclusion 2.
Yes.
Why?
Because there's like when you cancel it out or whatever, it says 2 NO molecules. Oh, wait, actually, maybe not, because I think there's 2 H2 molecules. I
Well,
don't know.
okay, all right. So I see that I see your reasoning is that you're kind of looking at what we've canceled out to get this overall reaction. So that's kind of an incorrect way of thinking about it. We're more worried about the mechanism, and the mechanism is these steps. We're saying, hey, this reaction has the mechanism of occurring in these 3 different steps. And one thing that this student is claiming is that based on the rate law and based on the mechanisms, 2 NO molecules are simultaneously at the same time colliding with an H2 molecule. So you're looking at the overall reaction. The overall reaction is not going to get us information about the mechanism and about the collisions that are occurring. So if I look at the mechanism, I can see that these NO molecules, they never collide at all with an H2 molecule, do they? Look at the mechanism. First, quickly, I have NO molecules that are colliding with each other to form this intermediate. And it's the intermediate that then collides with an H2 particle, isn't it? Does that make sense? So his claim number 2 is therefore incorrect. The collision between NO, and H2 is not simultaneous. They do not simultaneously collide, and actually they don't collide at all. NO and NO collide with each other to form N2O2, and then that collides with an H2 to let the reaction keep going. Does that make sense? So we like his conclusion 1, it is third order, but his conclusion then about the collisions that are happening is incorrect because he's forgotten about the intermediate. Does that make sense to you all? All right, part D, let's see. Ms. Majid has a question. Could you use the moles to determine the statement being false? Because for every 2 moles, Ms. Majid, no, you cannot, because once again, we're not worried really about this. His statements are about the mechanism. And this does not tell us at all about what's really colliding with what. It's only these steps in the mechanism that are telling us what has to collide. So no, that would be faulty reasoning, Ms. Majid, to say that, well, the stoichiometry here says 2 and 2. His claim is just flat out wrong, because NO never collides with H2. According to the mechanism, NO collides with NO to form the intermediate, and then it's the intermediate that then collides with H2. Does that make sense? So Ms. Majid, that would not be a good explanation. And Ms. Young, I think I just did repeat it, so hopefully that helped. Okay, excellent. Oh, Miss Cashman, do you want to try to explain part D? Why would increasing the temperature increase the rate constant K? Miss Cashman, any thoughts?
Maybe because whenever you increase the temperature, you increase the number of collisions. I'm not really sure though.
Nope, that's perfect. So we know that increasing the temperature is going to cause the particles to move around more quickly, therefore increasing the number of collisions. You could say that. You could also say that increasing the temperature allows more collisions to overcome the activation energy barrier. Increasing the temperature gives more particles, more kinetic energy to collide with enough kinetic energy. Does that make sense? So according to our rate law, which is here, the only place that can show up, the only place those changes can show up as affecting the rate is in the K value. There was a slide in the lecture where I talked about something called the Arrhenius equation. Do you guys remember that? The Arrhenius equation shows how K is related to temperature and to activation energy. You don't have to know or memorize the Arrhenius equation, but you do need to know conceptually that K in your rate law, whether it's a differential rate law or an integrated rate law, K has wrapped up in it those considerations about temperature and activation energy. By increasing the temperature, we know the rate is going to increase. The only way that could work out in my equation is therefore K changes. So increasing temperature increases the rate constant K, because all those collision ideas are kind of trapped up in the rate constant K. How do we feel about that? Any questions? Okay, well, we have about 5 minutes. Let's see what other question we could use. You know what? I think that we will probably just look at some more of these tomorrow as part of our review. But hopefully you guys are getting the hang of these reaction mechanism ideas, and hopefully you're understanding the difference between a catalyst, an intermediate, as it shows up in the reaction mechanisms, how to look at a mechanism and write the rate law from it, and how to interpret these reaction graphs. I wonder if there is a good one for us to do in the super problems real quick, maybe. Whoops. Oh, I don't know if there's one that we could do quickly. You guys need to be working pretty thoroughly on this packet. Ooh, we can talk about this. Okay, so this is on the practice quiz that I've posted right here. We talked about this already. How do temperature in the presence of a catalyst affect how a reaction proceeds? So T2 is higher, right? It's a larger temperature because the graph has been shifted to the right and flattened. Higher temperature means that we get more particles overcoming an activation energy threshold. And then, as Mr. Roberts told us earlier, catalysts lower the activation energy threshold. So EA1 here must be without a catalyst. EA2 would be with the catalyst because the activation energy required has been decreased. It's easier for particles to cross that threshold. So this is catalyzed. This is uncatalyzed. Okay, you know what? Let's stop there. So here's what you guys need to be doing. You need to be working on the lab report. I'd be happy to take questions over the lab report tomorrow. You need to be working on this packet. You all have that dumb assignment I posted due at the end of the day today, where you talk to me about how you've been getting outside and enjoying the sunshine. So please do that. It's super important for you guys to be moving your bodies and not just sitting staring at screens all day. I was in such a terrible mood yesterday because I was sitting and staring at a screen all day, and then I took a walk and everything was so much better. So you guys should get out and enjoy the sunshine and post something for me to tell me how you did that. That's an assignment. I'll make an assignment. This packet is due either in a Google Doc or pictures, due on Sunday night. The lab is due Sunday night. Tomorrow we will have a more in-depth, thorough review for the exam, and then we'll take the exam on Friday. And once again, that exam will require you to sit down and work on it from like 9:30 to 11 or 11:30. Let's see, questions about the packet. Do we have to have the practice quiz done as part of the packet? Yeah, Ms. Throwfall, it's simple questions. We've gone over most of them. So please do that as part of the packet, yes. All right, guys, sorry for the craziness. I appreciate your patience and your time as we figure out this whole e-learning thing. So my plan is from here on out just to keep doing this format where I post the lecture videos on the YouTubes. And then we'll have Zoom meetings every other day or so. We're breaking that pattern this week because our test is on Friday and I want to have another day of review. Mullet check, I guess, real quick. It's coming in nicely. I'm quite pleased with it. This is a quarantine haircut I gave myself. Not the best haircut I've ever had, but you know, for the apocalypse, I think it works pretty well. So. All right, any final questions, comments, cries of outrage, anything I can do for anybody? You're quite welcome, Miss Stark. Thank you.
I cut my sister's hair.
You what?
I cut Faiza's hair.
How did it work out? Can she show it off for us? Let's see your skin.
It looks fine, don't you think, Faiza?
It looks fine. Oh, fine is the word you use when it does not look fine, I feel like.
No, it looks good. It's different.
Okay. Mr. Roberts is asking me what do I think of Marty Robbins. I don't know who Marty Robbins is, Mr. Roberts. I'm so sorry to disappoint you. And Ms. Throwfall, I'm sure Henry will be back and you'll be seeing lots of him in the future, I'm sure. It is a fresh cut, Mr. Mullick. Thank you. All right, y'all. Thank you so much for your time. I will talk to you guys tomorrow at 9:30. See you.